Hello everyone, my name is Ouwen Jing, and I come from the School of Computer Science and Technology at Zhejiang University in China, where I am currently pursuing my PhD degree. Today, I'm honored to present to you our latest research. The title of the paper that I will be reporting on is Mapping Very Large-Scale Spiking Neural Network to Neuromorphic Hardware. My presentation will be divided into 4 parts: background, method, experiments, and conclusion. Firstly, I would like to introduce neuromorphic computing. It is an emerging computing paradigm that uses the spiking neural network model and has the potential to drive the next wave of AI. Neuromorphic computing is receiving increasing attention due to its characteristic of mimicking the brain and being energy efficient. An SS application is an attempt to use SNN to implement machine learning approaches. A neuromorphic hardware platform is a computer system specifically designed to implement SNN applications. These hardware systems can be uniformly abstracted as multi-core computing systems that use many homogeneous neurosynaptic computing cores to simulate neurodynamics in parallel. The most common design in the latest large-scale neuromorphic systems is network-on-chip with 2D mesh structures. The main advantage of this architecture is its high scalability to achieve massively parallel computing systems. Based on this multi-core architecture, SNN applications must be mapped into hardware. Mapping an SNN application into hardware means, firstly, partitioning neurons in SNN into several clusters to meet the hardware constraints, and secondly, placing these clusters in neuromorphic computing cores. And the mapping result can dramatically influence the performance of running of SNN applications, including power consumption, latency, and throughput. As shown in the table, the scale of existing neuromorphic computing hardware is getting larger and larger. Multiply new neuromorphic computing platforms, such as Loihi 2, Spinnaker 2, and Darwin 3, aim to reach capacity of tens of billions of neurons. Currently, researchers have proposed some mapping methods to map SNNs to hardware. However, existing algorithms lack scalability and are unable to efficiently map large-scale SNNs to neuromorphic hardware. To address this problem, we propose a novel approach to efficiently map SNNs to hardware. The approach consists of 2 steps. Firstly, it solves the initial placement using the Hilbert curve. Secondly, the force-directed algorithm is developed to optimize the initial placement. The Hilbert curve is a continuous fractal space-filling curve, first described by the German mathematician David Hilbert. It provides a mapping relationship between 1D and 2D space. We use the HSC as a guide to achieving an initial placement because it has some unique properties that are particularly suitable for mapping SNNs. One of the most important properties we want to introduce here is locality. The locality of HSC means 2 data points which are close to each other in 1D space are also close to each other after folding using HSC. Where SNN shows another form of locality, which means neurons are only connected to a few other neurons locally, instead of being widely connected in the whole network. Combining these 2 locality properties is that the neurons with connections will be mapped closely in 2D space based on HSC. which is favorable for the mapping problem. The HSC provides a placement that only maps clusters at a macro level, so there is a large room for local optimization. Therefore, we propose the FD algorithm to fine-tune the placement provided by HSC. The main idea of the FD algorithm is to regard clusters as particles on a 2D plane, and the connection between clusters as the tension. In this way, in the dynamic evolution of the physical model, particles subjected to greater tension will get closer, achieving the desired result. Clusters with greater connections will be mapped to closer position. In the algorithm, we first built a potential energy field to model cluster energy and system energy. Thus, the mapping problem is transformed into an optimization problem for solving the minimum energy of the system. We define force as the amount of energy that changes when a cluster moves in 4 directions, and further define the tension between pairs based on the definition of force. Based on the above modeling and definitions, we can give the basic workflow of the algorithm. Firstly, calculate the tension of all pairs. Secondly, sort these pairs according to the tension. Thirdly, some pairs with high tension will be swapped. Finally, repeat the first 3 steps until the algorithm converges. Here, I want to highlight a few points in the design of the FD algorithm. Includes checking before the swapping process, which guarantees the convergence of the algorithm. Hyperparameter lambda, which balances the efficiency of the algorithm with the quality of the solution. And introducing of the list of affected clusters, which significantly reduce the algorithm overhead when approaching convergence. All of these special designs make our FD algorithm run very efficiently. In the experimental part, we compare our method with other most advanced mapping algorithms. The evaluation matrix includes system power consumption, latency, congestion, and algorithm execution time. We presented a very large benchmarks, with the largest SN application having 4 billion neurons, which is more than 200 times larger than previous researches. Experimental results show that our method has significant advantage in execution efficiency. It can shorten the solving time of the previous method, which needs more than 100 hours, to only 10 seconds. The results show that the quality of the solution obtained by our algorithm is significantly better than the existing algorithms in each metric. In average, compared with the best results of the other 3 methods, our algorithm reduced energy consumption by 47.8%, average latency by 31.7%, maximum latency by 36.5%, average congestion by 42.9%, and maximum congestion by 36.7%. In fact, all existing methods have basically failed to provide reasonable solutions when SNN reach the scale of millions neurons. In conclusion, we proposed an approach based on Hilbert space filling curve and force-directed algorithm to map very large-scale SNN applications to neuromorphic hardware, achieved the state-of-the-art performance in both solving speed and quality of the solution. My presentation comes to an end. Thank you for your attention, and I welcome any questions or feedback you may have.